Hello all, and thank you for joining us today in this online presentation of Team B29's Senior Design Project. My name is Andres Flores Martinez, and my teammates are Brian Lee, Matthew Ramos, and Sean Turner. In this presentation, we will be covering the following topics: the background, the project statement, the needs placed by our customer, the desired technical specifications, how the global outbreak of the novel coronavirus changed the scope of our project, the final design, which includes a short video demonstration, the economic analysis of our finished project, and the project legacy and our vision for future iterations of this project. Finally, we will end with references and discuss the best method for you to voice your questions and give us feedback.
In the field of adaptive sports, there is little to no research done on injuries that typically occur while playing these sports. This is due to society revolving almost solely around the needs of those who are able-bodied. Consequently, this field is completely open for engineers, clinicians, and others to conduct developmental research to drastically affect the way paraplegic athletes can play sports without constantly risking injuries to other parts of their body. Currently, there are no universal requirements for sled hockey sticks aside from basic requirements required by USA Hockey. Many sled hockey players make their own sled hockey sticks from standard hockey sticks, causing a major variety in sled hockey stick types and lengths. In order to limit the scope of this project, the need for hockey stick optimization as it relates to soft tissue injury will be the focus. Many sled hockey athletes depend on their arms for mobility. Overuse injuries affecting the arms can be extremely debilitating to these athletes and can severely affect their quality of life. Being afflicted with a tissue injury that affects their movement can lead these athletes to being completely dependent on others. Therefore, this project proposes to create an instrument and stick that will measure the forces applied by the athletes during sled hockey and track how these forces react on the shoulders of the athletes by May 2020 with a budget of $1,500.
Here we have some of the most important customer needs. First and foremost, the solution must be able to measure the forces applied to it by the user. In order to optimize stick length, data must first be collected on the forces applied to the stick and how that force translates to the shoulder joint. The solution must also be compliant with the hockey stick guidelines set forth by the USA Hockey Federation. According to the 2019-2020 Sled Hockey Rulebook, no player's stick shall exceed 100 centimeters from the toe to the pick end of the shaft. The shaft shall not be less than 2 centimeters and no more than 2.8 centimeters. The blade of the player's stick shall not exceed 32 centimeters in length and 7.5 centimeters in width. By not deviating from these guidelines, the user should be comfortable in swapping from their usual equipment to this device. Finally, it must be able to function in game-like conditions. For the most accurate data collection, the user should be comfortable with the solution without changing playstyle to accommodate the stick. While not meant for live gameplay, the solution must be able to withstand game-like maneuvers such as quick acceleration/deceleration and sharp turns. Since its application will be on an ice rink, the solution must also be able to operate at low temperatures. Listed here is the technical specifications chart, which was developed to address the customer needs that were gathered from interviewing our project sponsor and observations made during visits to the Admiral's team practice. From left to right, the columns are ordered by the metric number, the corresponding customer needs number, the specified metric, the importance rating, the units, and the value. The importance rating to the right of the metric column have values ranging from 1 to 5, with the value of 5 being of highest priority and the value of 1 being of lowest priority. The value column on the right denotes the maximum acceptable range of values pertaining to that specific metric. Some of the key metrics here include the ability to measure force, product safety, and comfort/ease of use.
The coronavirus pandemic brought about a new set of challenges to the completion of our project. The team got split up across the country since classes went online and we returned home. This prevented us from completing some key steps to meet our target specifications. We were no longer able to use the MTS testing machine for calibration since Engineering Hall and the Human Performance Research Center was closed to all students. This also meant that we could no longer hold in-person trials since all sporting events were canceled. The use of 3D motion analysis was also no longer available or feasible without the access to the software or a test subject. We also faced some supply chain issues, with components like Zapp's glue used to mount the strain gauges being back-ordered until mid-May. However, through the help of our faculty advisor Dr. Schmidt and Dr. Goldberg, we were able to combat some of the challenges. We were able to obtain the material needed to mount the strain gauge, and we were able to perform a basic calibration using a set of dumbbells. Finally, we were able to create a 2D static analysis program on MATLAB using pictures taken from previous team practices and measuring them to calculate the angles and the lengths of segments. As stated in the previous slide, we were able to create a 2D model based on pictures like the one on the right, which was taken during a Milwaukee Admirals team practice. Players were asked to stand in the goal line and skate across to the other goal line. Cameras were set up at center ice to take pictures of the players in the sagittal plane. Pictures were broken up into 3 segments, as seen in the image on the left, and labeled AB for the stick, BC for the forearm, and CD for the upper arm. A force was placed at A in the direction of the beam, and these schematics were put into the MATLAB script, which I will explain. The MATLAB script works by taking the inputs of the lengths of each of the 3 segments listed previously. Each line in the input has a simple reminder of the measuring convention needed for each subject. Additionally, the input window also asks for the measurement of the angles between each of the segments as well as the input force in newtons. The program takes these calculations and outputs the resultant forces and moments of the elbow and shoulder joints in the output window. It is important to note that the program assumes no slipping or friction and does not take into account the weight of each of the members. In a future iteration, the input force could be given by our instrumented hockey stick, which Brian will describe next.
For our final design, the strain gauges used are planar 04590 rosette pattern strain gauges. Rosette strain gauges allow for measurements in multiple axes. The design focuses on strain measurement on a bending beam. Using these gauges in a Wheatstone bridge configuration allows for the HX711 breakout board to measure the change in resistance. Having 4 strain gauges allows for increased sensitivity and decreased interference within the circuit. A full bridge design with 4 strain gauges, each at 45 to the main axes, has a high output signal, a very good common mode rejection, and most importantly compensates for temperature effects. On the forward side of the stick, one gauge named SGXY on Rosette A is oriented in an XY axis. In addition, on the outward side, Rosette B has 3 gauges orientated in the X, Y, and Z axis. On the full bridge, both excitation and output signals can be inputted into the HX711 breakout board. The HX711 is a load cell amplifier that allows the microcontroller to read the changes in resistance as explained previously. Using the microcontroller, such as an Arduino Uno and the HX711 library, a measurement of weight in kilograms can be calculated and be converted to force. Currently, the microcontroller can display real-time calculations over serial to the serial monitor of the forces being applied to the hockey stick.
This slide contains a video demonstration of our final design. Please click on the play button in the video, and if that doesn't work, the recommended link
is in the comments. Please play at the highest resolution so that you can get the full appreciation of some of the screen items towards the end of the video.
For the economic analysis, the first thing our team analyzed was the developmental cost of the project. The development cost was divided into two parts, labor costs and parts and services costs. Since the labor was provided only by members of this senior design team, it was not charged to the total cost of the project. Now the table above shows the labor costs for designing, constructing, verifying, documenting, and installing the final prototype. It shows that 435 hours is the total time needed to complete the project. Based off the salary of $44.03 from the mean hourly engineering salary from the Wisconsin Bureau of Labor Statistics, the total labor cost was calculated to be $18,722.40. The next thing we looked at was the bill of materials. The table above outlines the components used in the final design of the instrumentation of the sled hockey stick. This bill of materials includes the materials that were used in the production of the revised final prototype and does not include any shipping costs. In addition, however, it also includes the cost of unused components that would have been used in the initial final prototype. In total, the bill of materials was calculated to be $619.19. The instrumented sled hockey stick was created solely to check the forces on the arms of the athletes generated during sled hockey. As we analyzed the potential market for our product, we concluded that there is a large market that is essentially untapped. To elaborate, there are 12 national Paralympic hockey teams, as well as NHL hockey teams having sled hockey team affiliates. For all these teams, there is a severe lack of data and research available surrounding the potential injuries that sled hockey players face. Our data can be paired with other 3D motion capture analysis tools that can ultimately result in a better understanding of how and where strange injuries occur. From this, we conclude that the data our device brings provides immense value to players, coaches, and team doctors. Looking at the estimated project cost, we concluded that since there is an ease of access to wooden sled hockey sticks for the team doctor of the U.S. Paralympic hockey team, it's safe to assume that the bill of materials will remain $619.19. If instrumented sled hockey sticks were mass-produced, an electrical assembler would be paid approximately $17.83 per hour in accordance with the Wisconsin Bureau of Labor Statistics. Under the assumption that it takes 30 minutes to assemble one instrumented stick, the labor cost would then equate to about $8.92 per unit. In addition to labor costs, overhead expenses were also considered in mass production. Under the assumption that there is a 10% overhead, which includes the components to make the parts, the base price of the product, the cost of electricity, factory space, and indirect labor, that calculates to be $62.81 per unit. The total cost for one instrumented sled hockey stick would then be $690.92, an extremely low price for technology that provides its users with real-time data to assist with injury prevention. Our sponsor, and potentially the U.S. Paralympic hockey team, will benefit from the data retrieved from the sled hockey stick as well as the 2D shoulder force calculator. As stated previously, the data will allow our customers to accurately determine the forces that are applied on the arm. With the help of additional calibration of the instrumented hockey stick, the customers will also be able to accurately determine what type of motion causes the most strain on the player's arm. Additionally, with the use of a force plate, customers will be able to input forces measured into the shoulder force calculator to better understand the magnitude of the forces applied at the shoulder and elbow joints. Ultimately, these benefits will lead to a reduction in injury and a higher quality of life for sled hockey athletes.
Based on the table on the slide, we see that most of the initial criteria was met. The few items that failed or were partially achieved were caused by the strain of resources caused by the global pandemic. Some of the key specifications included the ability to set up the prototype to the point of being plug and play. The leakage current was able to be measured and were within a safe range of operation. With regards to the U.S. sled hockey standards, some of the specifications were met, however, inspection by an official from the U.S. sled hockey governing body would be needed to certify it completely meets the standards. Most importantly, the ability to measure force with the finished prototype was achieved with the calibration of strain gauges. With a total cost of under $620, we were able to stay within the $1,500 budget.
As a team made up of 3 biomechanical engineers and 1 electrical engineer in our final year of college, we were able to complete a modified version of the instrumented sled hockey stick as previously planned. As we stated previously, we had to make drastic changes to our final design due to the COVID-19 pandemic. Prior to being forced to change our project scope, there were several ideas that were extremely important for the next senior design team to be aware of. First, sled hockey practice and being in constant communication with Dr. Uline provided a huge benefit in increasing our knowledge and understanding of the pains that sled hockey athletes go through. We were able to build relationships with players who ultimately agreed to assist with testing. Additionally, an important aspect of our project was consulting professionals not initially related to our project to give us more in-depth knowledge on what we were actually researching. David Newman helped provide us with some great knowledge on strain gauges, while Dr. Kenneth Lee, who specializes in physical medicine and rehabilitation, assisted us during our brainstorming stages, helping us narrow down the scope of our project so we had realistic expectations. The last important part of our project was finding a way to create and connect a MATLAB program to the outputs of the instrumented sled hockey stick. One obstacle that our team faced throughout our project was time management. Since the team was made up of entirely graduating seniors, we were all trying to juggle a multitude of things like managing our difficult classes, preparing for life after graduation, like going to job interviews and career fairs, and our personal extracurricular activities. After doing a low-quality job on our first project schedule, we ended up creating one that was much more realistic with our time. Paying close attention to our schedule really helped us stay on top of various deadlines. Another unexpected obstacle has been the COVID-19 pandemic. It's thrown a huge curveball in all of our initial plans for the project. To really stay on top of things, we committed ourselves to meeting multiple times a week in order to try and stay on top of various deliverables that were still due. On the technical side of things, our team faced 2 main obstacles that are closely related to each other. First, no one in our group had prior experience on the proper process of mounting strain gauges, nor did we have any of the materials. After further research, even if we were to mount the strain gauge, we were still unsure about the type of material to use for the instrumented stick, since wood is naturally isotropic material. This means that its properties vary with grain direction. As a result, we were ultimately directed to David Newman, and at the meeting, we concluded that for the purposes of our project, wood would give us proper results. Additionally, David Newman also agreed to assist us with properly mounting the strain gauge. However, after the rise of the COVID-19 pandemic, he instead gave us some of his industrial adhesive as well as a list of instructions on how to properly mount a strain gauge on the stick. These obstacles forced our group to really think outside the box and reach out to consult other professionals on concepts that we were not familiar with.
Further looking on the electrical design of the stick, the team looks forward to having the next group take on these goals. Regarding electrical components, the team should be able to create a custom PCB board to seamlessly connect the Arduino Nano, HX711 breakout board, microSD expansion card, and the Wheatstone bridge. We would suggest a program like Eagle. This would allow the stick to be functional in practices and experimentation, where players can test its functionality without hindering performance. Referring to the goal of collecting data wirelessly, we had intensely wanted to do wireless transmission over Bluetooth, however opted to go for storing data from the Arduino in a micro SD card. This would allow for easier methods of data transportation and less complications for the conductors of experience at the VA. Lastly, we hope for the next members to implement storage capability with the current code of the Arduino. With both a custom PCB and internal storage, the components would be able to be housed in an external 3D enclosure on the player or on the stick itself.
Thank you for listening to our presentation. We hope you enjoyed learning about our senior design project. If you have any questions, please feel free to reach out to us via email or ask a question in our Microsoft Teams channel. We will be happy to respond in writing or set up a call to discuss items if needed. Once again, from all of us on Team B29, we want to thank you for your time and your interest in sled hockey.